Hey everybody, welcome back to another video. So today I'm really excited to talk about this. We're going to be going into our new HA iSCSI solution that we've been developing for the last while, and I'm really excited to finally show it off in real time here. We're also going to be teasing some really cool things about Houston and some new modules, but I'm going to save that to the end of the video because I really want you to watch the whole thing. Also, I'm going to be diving into iSCSI in general because I want to set the stage and make sure everyone kind of understands iSCSI. So we'll do a little precursor about iSCSI in general before we dive into our new solution. So come on in for the ride and let's do it. All right guys, so before I dive into the HA iSCSI solution that we've been developing, I'm going to talk about what the status quo of iSCSI is as well in the Linux world as well as in the Ceph world. But before I do those things, what I want to do first is get through some of the naming conventions that iSCSI uses. I don't want to be using words and kind of just sound like I'm talking Greek to you guys, so I want to make sure we're all kind of on the same field of what terms mean. So in the iSCSI world, what you're essentially doing with iSCSI is you are plugging in a hard drive or a set of blocks over a network. Same way we think about SMB and NFS, you're plugging in a file system across a network. iSCSI is a same concept, but doesn't have a file system layer. So if you were to just put a hard drive into your Windows machine and then you put your file system on it, they would be doing a similar thing, but with iSCSI, but over the network. So the pieces that are involved in the iSCSI framework are as follows. First, if we talk about our iSCSI server, the actual machine that hosts the block that's going to be exported, we call that a target. So that's your iSCSI target. And what that target has is it has LUNs, logical unit numbers, and what LUNs are essentially the disks that you're going to be sharing out over the network. So on your target, you've got your LUNs, those are your actual disks. And then from there, what you have is you have portals. And your portals are your IP addresses on your server, on your iSCSI target, that are actually going to be listening for iSCSI connections. Because your iSCSI server may have 4 or 5 IP addresses and you may not want all of them to be doing iSCSI. So that is what our portals do. And then we could also have something called ACLs, and that is essentially where we have the IQN, the iSCSI qualified name of a client. And that allows them to say, I'm allowing this client to access these LUNs. So that gives us the ability to essentially lock things down and say, maybe I have 3 clients, or initiators in this case, and I only want one client to access this LUN, and I want the second client to access all the LUNs, etc. So you have the ability to lock that down. Then on the client side, that's actually consuming the storage, the concept we have, again, is the initiator. They're the initiator. And why we call them initiator, it seems kind of backwards, but in this case, the initiator is the one that actually sends all the SCSI commands. Whether it's I'm sending a read request command or a write request command, it sends the commands, and that's why we call them the initiator. So let's just recap. The initiator is essentially a client. The target is the server. The portals are the IP addresses, the LUNs are the disks, and then the ACLs are essentially where you put your initiator, your clients, and it tells you which clients can access which LUNs. So that's the whole thing. And then the last one, IQN, iSCSI qualified name. Every single target and every single initiator is going to have one of these IQNs, and that is essentially the naming scheme that tells you who you are. So everyone will have a unique different IQN, both servers and clients, both targets and initiators. So those are all the pieces, and I want to make sure that we got that out before we went on. So hopefully I explained that good enough. We'll put some B-roll up as well. Hopefully it helps. But from there, let's move on. So what is the de facto iSCSI solution in Linux? Well, that is something called LIO, or Linux IO subsystem, target subsystem for Linux. And this was the default iSCSI solution that was chosen quite a long time ago now by the Linux kernel developer community to say this is our supported iSCSI solution, even though there actually is more than just that. But if you were to just install iSCSI on a regular Linux machine from repos, that would be the one that you would get. And that comes with a really cool command line tool called Target CLI, and it lets you set it up very, very easily. And it's quite good actually. It's really easy to follow. They have a nice text user interface, but there's actually other solutions as well, and we'll get to those. Okay, so that's the single server, that's the Linux iSCSI solution. Well, what about Ceph? What does Ceph use for iSCSI? Well, Ceph developed something called the Ceph iSCSI project, which uses LIO at the lowest level. So it still uses the regular iSCSI solution that's implemented in Linux. So they didn't reinvent the wheel there. But what they did do is they developed a user space tool that allows us to translate Ceph's librd commands. So an RBD is Ceph's block storage protocol, and RBDs can be mapped with a kernel mount, so they map physically to the host, or they can be done through librd, where you're just sending system API calls over librd back and forth to the Ceph cluster. And that's what they settled on. That gives some flexibility, but because that means we're operating in user space and not in kernel space, it does incur some latency overhead, and performance does suffer a bit from that. So that's one thing, and beyond that, it doesn't also support something that we call persistent reservations across multiple hosts. So what is a persistent reservation? Well, if you have multiple initiators, so clients of iSCSI that are going to be accessing this block storage, sometimes they have to access it in unison. So what I mean by that is we know that file systems can be shared out and multiple clients can access the same file system, but there is no native way for block storage to do that. So block storage is meant to be consumed by a single host. So if you mount a hard drive on a Windows machine, and then you mount that exact same hard drive on another Windows machine, those two Windows machines don't know anything about each other, so they could very quickly corrupt the data of each other because they're both writing to the same disk. But what we can do with persistent reservations, if all initiators are all in a cluster and they all are in agreement, we can use persistent reservations to make sure that that data does not get corrupted and all of the clients or initiators can consume the exact same block device in a clustered method. So that's really cool. Okay, so that is the Linux solution, that is the Ceph iSCSI solution. So they use that TCMU runner, which is essentially just a shim, right? It's a user space shim. It talks back to Linux IO, and then it also talks back to the Ceph cluster. It acts as a go-between of the kernel space and the Ceph space, which is really, really cool. There's also two other pieces, RBD Target API and RBD Target GW. These services, what they do is make sure that the actual iSCSI configuration is the exact same on both hosts. So if you change the configuration, let's say you added another LUN, it needs to make sure that both of your iSCSI servers, or even more if you have more than two, are all going to get that update at the exact same time, and they're all going to stay in lockstep together. So that's a really cool thing too. The RBD Target GW will do it individually on each host, and the API will do it globally. Okay, so that is Ceph in a nutshell. So why don't we use it? Well, there's a few reasons. ESXi, and I'm going to give a big shout out here to Linbit. Linbit are the developers of DRBD. If you've ever heard of DRBD, or even if you haven't, stay tuned because we're going to be doing some really cool content with DRBD soon and with Linbit. We may even have some of the Linbit engineers on the podcast. So with DRBD, what they were able to figure out is that the default LIO, Linux IO, SCSI subsystem actually has some issues with ESXi and vSphere where you get some really weird timeouts that should not occur. We've actually experienced that as well with some customers here, and so they gave us some really, really good data to show that it was happening and why it was happening. So that was awesome to see. Now, again, another big shout out to those guys. What they have done and what a lot of other storage area network appliance vendors have done have shifted to SCST. And what SCST is a completely other solution to do iSCSI in Linux. It's not in the kernel like LIO is, but it is a kernel module with user space tools just like Linux IO, and you can load it in and you can compile and install the packages yourself. So SCST is really, really cool. We've actually seen in some cases it's a little faster as well, and it doesn't have any issues with ESXi, which, if we're being honest, the #1 use case for iSCSI for our Ceph environments is ESXi. For many other use cases, we can use native RBD. Even Hyper-V and Windows has native RBD support these days. So really it comes down to ESXi being our biggest consumer of iSCSI. And so it's a big deal that we're now be able to use SCST instead of LIO that doesn't have these odd timeouts at certain opportunities and certain times. So what we built was a highly available iSCSI solution built on SCST with Pacemaker, Corosync, as the back end. So Corosync is what keeps everything in time, and Pacemaker is what is essentially the process that's making sure that we can keep our resources HA. It activates the resources, it moves the resources, etc. So what I'm going to do is I'm going to show you what we built, and we'll just dive right into it, and you can kind of see all the pieces of this solution, and we'll even show it in action, maybe doing a failover. So let's check it out. So as I said, we've been developing this and testing this for quite a while now, so I'm really excited to show this off. So first things first, I'm going to show you, set the stage, what the environment is right now. So I have a Ceph cluster right now that is an all NVMe Ceph cluster. We got quite a few OSDs here, 96 NVMe OSDs, so quite a fast Ceph cluster. We've got all 100 gigabit networking, and so what I have is I have two bare metal iSCSI servers, and they are in a Pacemaker PCS cluster, and they are what provide iSCSI. It translates the Ceph native RBD over through iSCSI for our clients. In this case, my client is a Windows machine rather than an iSCSI because it's just for the specific testing that I'm doing for one customer. They're using Hyper-V and clustered shared volumes, so that's what's most important to them. So let's take a look here. If I do a PCS status, we can take a look at our cluster. And again, I'm going to give another big shout out to Linbit here, because what I built here, I didn't reinvent the wheel, I'll tell you for sure. A lot of the work that was done was reused from stuff that they figured out for their DRBD solution with highly available iSCSI. So I just adapted a lot of that work to make it work with Ceph and specifically for our environment. So again, amazing work on their part. I've just used their documentation, which is fantastic. So let's take a look at what we've got as resources in our Pacemaker cluster. So we can see we've got 4 RBDs. So we are using the RBD resource package for Pacemaker or PCSD. And what OCF resources are essentially at the end of the day is they're just a set of bash scripts that run a set of commands based on what you want them to do. So for example, we've got in this case RBDs. So for every one of our RBDs that are being used in this iSCSI solution, we have a Pacemaker resource that manages them, and their entire job is to mount them on the active machine and unmount them when it's moving to the other machine, and then mount them on the new machine. So it just manages the mounting and the unmounting of RBDs. Then we can see those are outside of a group, but then we have a group that's called Bare Metal SCSI Group or SCST Group. And inside of that group, we have a set of other processes. The first one is a port blocker. I'll get to what that is, and it turns the port block on. The next one is our VIP, so that's our portal IP that's going to fail over between hosts, because if the iSCSI client or initiator is connected to the VIP portal and it's currently on iSCSI 1, if iSCSI 1 fails, we need that portal IP, that VIP, to fail over to SCSI 2 so it can continue operation, and so the client doesn't actually know that anything happened, that there was any failures. In many cases, you might want more than one VIP if you're using multipath I/O. In this case, we just have a single path going to our iSCSI initiator, but it's very, very viable to do 2 or more. Then we have an LVM resource. So in this case, what we're doing is we are taking 4 RBDs, we're striping them together into one, or making them into a VG, and then we're striping a 4-stripe LV out of it. And that gives us some better performance again. It even improves performance higher. And it allows us to add additional RBDs to our LV without having to increase the size of them. But we can also increase the size too if we want, instead of adding more RBDs. It just depends on what your goals are. And then we can see we have our actual iSCSI target. So this is our highly available iSCSI target, and every one of these resources are just things that are going to move, and that's why they're added into the cluster. Anything that's here is being managed specifically by Pacemaker, and during a failure scenario, what they're going to do is they're going to stop all of these resources on the active machine, and then they're going to restart them on the other machine, on the what was a secondary but will turn into the active. So we can see we have our iSCSI target, so that has a configuration in it. It has the IQN, it has the portal information, and then the next one we have a LUN. So this is our one LUN that we're using that is tied to that logical volume, that LV. And then finally we have a port block off. Okay, so what does port block on and off mean? So during a failure scenario, The order of operations are going to go in the order of your resource group and the order that they're added. So it's very important that you have a proper order of how things fail and how things restart. So when you fail over, the first thing that's going to move is your RBDs. Your RBDs are going to mount on the secondary host. Then the first thing to come alive is going to be port block on. And what that does is that blocks the iSCSI 3260 port on the new host that's going to be the active host. The reason why we do that is because as the VIP fails over, the initiator or the client will immediately try to reach out on that VIP and try to access port 3260 or the iSCSI target. But at this time, because it all happens in such quick succession, it's possible that the iSCSI target has not failed over and has not moved over yet. If that happens and the initiator tries to make a connection, but there's no iSCSI server there, it says, oh, there's nothing there, connection refused, and it just gives up and it fails. So we never want that to happen. So what we do is we block that port momentarily. Everything else fails over. The VIP fails, the LVM, the target, the LUN, and then finally port block off, unblocks that port, and then the client goes back in and everything goes back to normal. So that's the pieces that we have in all of this. And so let's take a look. So we've got a Windows client here. We can see if we take a look at our targets, we've got, and this is our IQN. So this is the format of the IQN. IQN.24-05, 45 drives bare metal. And so we can see that we're connected. Also, we can see that we have one disk, iSCSI here, that's 1 terabyte. So that's great. And so if I go to my directory, I'm going to open up the iSCSI share, and I'm also going to open up another folder, and we're going to start copying a file over. And when I start copying the file over, what we're going to do is we're going to force a failover, and we're going to see how it responds to it. So let's go to our RAM disk here. I'm going to copy the file to the RAM disk very quickly. And we can see we're reading from the Ceph cluster, the iSCSI array at about 1 gigabyte, 1.5 gigabytes a second. So quite fast for single-threaded iSCSI, especially with Windows File Explorer, single-threaded. Okay, so we've got our file moved. I'm going to delete it from the iSCSI. Let's even start a video. So we've got a video inside of our iSCSI here. I'm going to start playing, and I'm going to mute the sound. There we go. So we can have that playing. So it's going to play. So we'll know immediately when I/O pauses because the video is going to pause. So let's get this ready. I'm going to push this over to the side, and I'm going to grab our iSCSI environment. I'm also going to do a watch PCS status. So we can see that everything right now is running on iSCSI 1. So the iSCSI 1 server has everything running on it. Okay, so I'm going to get ready on iSCSI 2. I'm going to go PCS node standby BM SCST 1. And what this is going to do, it's going to put the active iSCSI server in a failure state, and everything is going to have to migrate. So before I do it, though, let's start our file transfer as well. So let's take our test file and let's copy it into our iSCSI volume. Okay, so there it goes. All right, so let's start it. So node standby. So there we go. We can see that our iSCSI LUN is stopping. So sometimes this takes up to about 65 seconds. There's two failure scenarios, two main ones. One is instant, where pretty much even if there's I/O happening, it instantly will fail over pretty quick within about 5 seconds. And the other one that we've noticed is this scenario right here, where it ends up taking about 55, 65 seconds before the failover actually occurs. But that is well within the realm of timeouts for the iSCSI solution, so it'll have no issue. So what we're going to see is we can see that the transfer is paused. We can see that the video has also paused. And we're just going to sit here and we're going to wait for this to finish failing over. And then it will just continue and pick up as if nothing happened. All right, so we can see that everything has failed over to BMSCS2. Everything has resumed here on this guy. We can see my video is still going, and our transfer just completed. So that is well within the time that is acceptable for iSCSI to fail over. But let's try to fail it over back the other way and see what happens. So what I'm going to do first is I am going to unstandby BMSCST1. All right, okay, and so we can see now we've got everything is now moved over to SCST2, so our second server, which was our secondary, it's now our primary. But now let's go the other way. Let's move from the secondary back over to SCST1. So we'll keep this video playing in the background, and let's go again. So PCS node standby, SCST2, hit enter, and we'll watch it go again. And look, so what we're seeing here is the other scenario. See how fast that was? It was able to fail that over. So we did get a little pause here, but we're gonna see how quickly the video resumes because everything has already failed over to SCST1. So that's the ideal failure scenario that we would love to see. And there we go. Our video has started back already, continuing on just like nothing happened. So that's essentially the long and short of the new iSCSI solution that we have. So if any one of our customers watching this and you are interested in iSCSI, you're interested in testing out a new HA iSCSI solution, definitely reach out to us because we will be rolling this out in the near future. Another big teaser that I want to talk about, we are developing an iSCSI module for Houston. So that has been a long time coming. And I'm really excited to announce that it is going to support clustering as well. So we're going to have the ability to build a HA cluster like this within the Houston UI for iSCSI. And it's going to support single server ZFS. And it is all going to be using SCST, not Linux IO. So that's another really cool announcement as well. So yeah, hopefully you enjoyed this video. If you have any questions, don't hesitate to throw them in the comments. And thanks for watching, guys.